Uh, I'm just setting up my chart right now. Okay, so as the title suggests, I'm going to be studying calculus, and the resource I will be using is OpenStax. Basically, this is a free open resource, and they have a ton of books. You can see the subjects over here. I'm going to select maths, and they have various different maths topic. They're all at a university level, like up to a university level, and they're all free. So let's take one. Since we are studying limits, let's do calculus 1, table of contents, and limits introduction. So I'm going to be doing exercises and I'll be using this. I'll be also collecting my notes there. So it takes quite a while to load. Okay. I'm going to skim read since I've already studied limits. I'm just going to skim read the topic. The idea of a limit is central to all of calculus. We begin this chapter by examining why limits are so important. Okay, I'm not sure why my mouth wasn't moving. Then we go on to describe how to find the limit of a function at a given point. Not all functions have a limit at all points. So let's just go next. A previous calculus. Learning objective. Describe the tangent problem. Explain the idea of a limit. Let's just go. The tangent problem and differential calculus. Rate of change is one of the most critical concepts in calculus. We begin our investigation of rate of change by looking at the graph of three lines. Minus 2x minus 3, x over 2 plus 1, and 2. As we move from right to left along the graph of minus 2x minus 3, we see that the graph decreases at a constant rate. The rate of change is determined by the slope minus 2. Similarly, the slope of half in the function g of x tells us that for every change in x of 1 unit, there is a corresponding change in y of half unit. And h of x has a slope of 0. Okay. Compare the graphs of these three functions with the graph of k of x is equal to x squared. The graph of k of x is equal to x squared starts from the left by decreasing rapidly, then begins to decrease more slowly and level off, and then finally begins to increase. We might ask, how do we measure the rate of change of a nonlinear function? We can approximate the rate of change of a function f of x at a point a, f of a, on its graph by taking another point on the graph, drawing a line through the 2 points and calculating the slope of the resulting line. Such a line is called a secant line. Okay. This is an example of a secant line. We formally define a secant line as follows. The the secant to a function f of x through the points a and x is the line passing through these points. Its slope is given by this formula. And let me copy this. Let's see how well this works. Oops. I don't know what's happening. Let me reset the canvas. Let me copy this. Paste it. Okay, this is actually quite good. Is this? I think I should press Control Shift V. And all of this is a single element through the points. Okay. No. It's given by I will just write it out. Too thick. I'll zoom a little. Is there a way I can get rid of this? M secant. I'm just write M is equal to F. I think I will save my notes and I'll post it on Reddit. The accuracy of approximating the rate of change of the function with the secant line depends on how close x is to a. If x is closer to a, the slope of the secant line is a better measure of the rate of change. The secant lines themselves approach a line that is called the tangent of the function f of x. Figure 2.6. The slope of the tangent line to the graph at a measures the rate of change of the function at a. This value also represents the derivative of the function f of x at a, the rate of the function at a. This derivative is denoted by f apostrophe a. Differential calculus is the field of calculus concerned with the study of derivatives and their applications. Finding the slope of secant lines. I think I will do I will do this, and I will do all my workout over here. All my workout on the right side, and all my notes on the left side. I think I should. Oh, why do I see two lines? Hold up. And I will just use this. Okay, work out. Estimate the slope of the tangent line rate of change to x square at x equals 1 by finding the slope of the secant line through 1, 1 and each of the following points on the graph. Okay, I have a calculator with me. So the graph is x squared. I need to find it at x equal 1 to this point. So M is f actually 4 minus 1 over 2 minus 1, which is 3 over 1. Let's see, that's correct. Yes. I'm only deciding to do one of them since this is a revision. Estimate the slope of the tangent line. Already did something similar. Okay. Let S of t be the position of an object moving along a coordinate axis at time t. The average velocity of the object over the time interval a through t, where a is less than t, is this. If as t is closer to a, the average velocity becomes closer to the instantaneous velocity. We may define instantaneous velocity as follows. For a position function s of t, the instantaneous velocity at a time t is equal to a is the value that the average velocities approach on intervals of the form a to t or t to a as the values of t become closer and closer to a, provided such a value exists. Okay, a rock is dropped from height 64. Wait. A rock is dropped from a height of 64 feet. It is determined that its height in feet above ground t seconds later is given by this. Find the average velocity of the rock over each of the given time intervals. Use this information to guess the instantaneous velocity of the rock at time t is equal to 0.5. So this is the distance. This is the time, I think. Or am I getting this wrong? Which one is S? Hold on. I'm just using a calculator right now. I'm plugging the value of t. Square. Oh no, they're both t. Okay, let's see. Example 2.2. So S 0.49, SF 0.49, I just collected S of 0.5. S 0.5 is 60. Now I will do 49. Okay. 60.158. And the other one, last one, S 59. Now what do I do with this? I have to find the average, I think. So the average of these two. The average of these two. So this is 59.919, and the other one averages 60. I don't understand what they're asking. Oh, wait. No, no, no. This is wrong. I got these two distances. Then I have to divide them by the time interval. So this would be basically 0.5 minus this would be the time interval. $15.8. Now minus and for the other one 5. This is a 5. Hold on. Minus 16.2. I think instead of using my calculator, I should just do it on screen. This was liter. And the instantaneous velocity would be between those two, between these two, from what I understand. The area problem and integral calculus. Okay, let's skip the preview of calculus. And let's go to limits because that's what I'm here for. Also, let's just erase this. Is there a faster way to erase all this? Also, I just realized I can use middle click to turn. Let me see if I can do the same with my pen. Yeah. The limit of a function. Intuitive definition of a limit. Let's take a closer look at how the function, this function behaves. Hold on. Okay. Let's first take a closer look at how this function behaves at x equals 2. As the value of x approaches 2 from either side of 2, the values of y approaches 4. Mathematically, we say that the limit of f of x as x approaches 2 is 4. Symbolically, we express this limit as this. Okay, definition. Let f of x be a function defined at all values in an open interval containing a. With the possible exception of a itself, let L be a real number if all values of a function f of x approach the real number L. As the values of x is not a, but they approach a, then we say that the limit of f of x as x approaches a is L. Okay, let me write it on my notes. Control Shift V. Oops, I don't think I copied it. Yeah. think, wait, okay, symbolically like this. Okay, I could do this, but it's gonna take too long. The limit is 3, right? Yeah, limit here is -1. Two important limits. Let a be a real number and c be a constant. I'll write this in my notes. Two important limits. Limit like this, I think. Yeah. Oops. Then the other one. As we consider the limit in the next example, keep in mind that for the limit of a function to exist at a point, the functional values must approach a single real number value at that point. If the functional values do not approach a single value, then the limit does not exist. I think I'll write this in my notes. I'll make this line bigger. Keeping it bigger. Sometimes indicating that the limit of a function fails to exist at a point does not provide us with enough information about the behavior of the function at that particular point. To see this, we now revisit the function g of x modulus x minus 2, all of that divided by x minus 2. As we pick values of x close to 2, g of x does not approach a single value. So the limit as x approaches 2 does not exist. Yeah, I think I should open the graphing calculator as well. To provide a more accurate description, we introduce the idea of a one-sided limit. we see f of x is equal to so there is no limit because from both sides they don't approach a particular value, but we can do one-sided limits. For all values to the left of 2 or the negative side of 2, g of x is negative 1. Okay. For the positive side it will be plus 1. From the positive side it's plus 1. I'll take all this and write it on my notes. For the limit of a function to exist at a point, the functional values must approach a single real numbered value at that point. If not, then the limit does not exist. Wait, I didn't copy this properly. Cut this. Let f of x be a function defined at all values in an open interval of the form C to A, and let L be a real number. The values of the function of f of x approach the real number L. The values of x approach the number A, then we say that L is the limit of f of x as x approaches A from the left. I will write it. Symbol A minus limit x approaches A from the negative side. Here. Now for the right, I think it will be something similar. Let f of x be a function defined at all values in an open interval of the form A to C. Let L be a real number. The values of the function f of x approach the real number L as the values of x, where x is more than A, approach the number A. Then we say that L is the limit of f of x as x approaches A from the right. Symbolically, we express this idea as limit x A from the plus side L. For the functions f of x, x plus 1, x squared minus 1, evaluate each of the following. We can just do it here. x plus 1 at what? Less than 2, x square more than or equal to 2. How do I define piecewise in Desmos, if anyone knows? Minus 4. And I'm searching it at point 2. Aren't the limits same? Because they all converge. They all meet at point 2. Isn't it 3 for both of them? Did I write the graph wrong? Oh, it's minus 4. Yeah, this is 0. Then this would be 3. So a limit overall exists if it exists from both sides. I can write that here. So limit as x approaches a of f of x exists if and only if it exists from the negative side and exists from the positive side. Infinite limits. Evaluating the limit of a function at a point or evaluating the limit of a function from the right and left point helps us characterize the behavior of a function. Now we turn our attention to h of x 1 over x minus 2 square. Okay, let me see 1 over x minus 2 square. And we are evaluating at point 2, right? So at point 2, oops. Yeah, at point 2 it's positive infinity. We define 3 types of infinite limits from the left, right, and two-sided. And it could be positive or negative. Okay. I think I will write my notes at the end of the stream, like after I finish my stream. It is important to understand that when we write statements such as limit of f of x is positive infinity or negative infinity, we are describing the behavior of a function as we have just defined it. We are not asserting that a limit exists. For a limit of a function f of x to exist at a, it must approach a real number L. Okay. is this is the vertical asymptote. We should also point out that in the graph, 1 over x minus a to the power of n, points of the graph having x coordinates very near to a are very close to the vertical line x is equal to a. The line x is equal to a is called the vertical asymptote. Definition: let f of x be a function if any of the following conditions hold, then x is equal to a is a vertical asymptote. Okay, but can I highlight? I think I might need a school account to log in. Evaluate each of the following limits using infinite limits from positive integers. Identify any vertical asymptote in the following. What's this? Infinite limits from positive. Oh, I just read this. So if it's 3, it's gonna go downwards. The asymptote will be at this value. If I do a add slide, yeah, the vertical asymptote will be a itself. For odd numbers, it will go to opposite sides. For even, it will go to the same side. So x minus 2, vertical asymptote will be at x is minus 2. For all of them, it will be the same asymptote. Okay, behavior of a function at different points. X goes to negative 4 from the negative side. It's 0. From the positive side, it's also 0. Overall, it's 0. Then f of minus 4 itself is 0. B, from the negative side, it's approaching minus 2. It is 3. Even from the positive side, it's 3. And the limit, overall limit is 3, but it's not defined at negative 2. As for this, from the negative side, it's 6. From the positive side, it's 3. Overall, it's not defined, but f of 1 is 6. From as of x approaches 3 from the negative side, it's negative infinity. From the positive side, it's still negative infinity. Overall, it's negative infinity, and f of 3 is not defined. Hope I'm correct. Exercises. I think I will do exercise at the end of the stream. Or I can do it just now. Maybe end of the stream. Next. How many? How much content is there? Should I do the exercises now or like after I've studied the whole chapter? I don't know why this is not loading. Okay, table. Limit loss, continuity, precise definition. They have the answer key, right? Answer key chapter 2. Okay, we'll do the questions and I will look at the answer key then. For the following exercise, consider what's happening. For the following exercise, consider the function f of x squared minus 1 over modulus x minus 1. What do you result in the preceding exercise indicate about two-sided limits of f of x as x approaches 1? Oh, I have to fill this in. I don't have time for that. I'll just plug it in here. Square minus 1 and x minus 1. So the limit does not exist at 1. So look at the answer key. Number 31. Yeah, limit does not exist. For the following exercise, consider the function f of x plus 1. F of x plus 1. One over x. Okay, so the function is continuous, so the limit will exist everywhere, I think. It's trying to calculate the limit at 0, and it definitely exists at 0. Oh, yeah, it does exist at 0. Also, the limit, yeah. Okay. Most of it is about filling values. Let's do question 45. Limit a from the positive side, 1 over alpha cos pi over alpha. Let's use the scientific calculator now. One over a cos pi over a. F of 0.1, 8.5. Okay, it's not reaching a fixed value. Again, the answer key here. Hold on. Why is it 1000? Did I write it correctly? Oh, I think it's in... Yeah, this is in radians. So the limit, it's increasing infinitely. So the limit is infinity. Let's see. The following exercise, consider the graph of the function of y is equal to f of x shown here. Which of these statements about y is equal to f of x are true and which are false? So, as x approaches 10 plus 10, this is true. As x approaches negative 2 from the plus side, it is 7. It's not 3. Wait, yeah, it's not 3, so that's false. Negative 8. Nope, this is false. And x approaches 6. Is it positive 6? Yeah. Then it's 5. Nope, the limit does not exist. False. Okay. Number 51. X approaches 1 from the positive side. Then it's 2. And x approaches 2 overall. It doesn't exist. 51 and 53. Wait, hold on. This answer is wrong, I think. Limit is not supposed to exist because it's different on the positive and negative side. I mean, if I'm wrong, then someone should correct me. Use the graph of the function y is equal to f of x shown here to find the values if possible. X is equal to 0. X approaches 0 from the negative side, then it's 1. From the positive side, it's negative 4. Overall, it doesn't exist. And x approaches 2, it's 0. 1 does not exist. Okay. Next one. X approaches negative 2 from the negative side. Then the answer is 2. Sorry, the answer is 0. From the positive side, it's 2. And overall, it doesn't exist. Plus 2 from the negative side, it's minus 2. From the positive side, it's plus 2. And overall, it shouldn't exist. Let's do 63. 2. Yep, 2 is the correct answer. 0 from the negative side, it's plus 3. And overall, it doesn't exist. Okay. Zero from the negative side. They're both 0. 69, yeah. 0. Then 71. 0 from the negative side, it's minus 2. From the positive side, it's 0. Overall, it doesn't exist. And then x equal to 2. X approaches 2, I mean. It's 0. So 135 minus 2 doesn't exist and 0. Okay. You have to sketch a graph, never mind. Okay, shock waves arise in many physical applications, ranging from supernovas to detonation waves. A graph of density of a shock wave with respect to distance x is shown here. We are mainly interested in the location of the front of the shock. Label x SF in the diagram. X approaches SF from the positive side is rho 1. I will call it P. P1. And from the negative side it's P2, and then overall it doesn't exist. So the physical meaning could be that there's an instantaneous jump, like it happens too suddenly. Okay. Next one. Evaluating limits with limit laws. We already wrote this. Okay. Some law is that if you iron it from the inside, then you can take the limits separately and add them. Different laws, it's like the sum law but for the differences. Constant multiple laws, you can take the constant out. Product law, you can multiply them separately. Quotient law, okay, you can take the limits separately. Power law, for every positive integer n, and then root laws. Okay. We now practice applying these limit laws to evaluate a limit. Evaluating a limit using limit laws. Use the limit laws to evaluate this. So, I think we should just plug in minus 3 over here. So 4 times 3 is 12, which should be minus 10. Yep. We can just plug in 2, I think. 2x squared. Can I copy and paste? What happens if I do this? Can't select it properly. Nope, it doesn't work. 2x squared 2 times 2 is 4. 4 times 2 is 8. 8 minus 6, 2 plus 1, 3. And then 2 cubed, 8 plus 4, 12. So it's 3 over 12. Okay, just 1 over 4. Isn't it the same thing I did last time? Calculating a limit when f of x over g of x has an indeterminate form 0 over 0. First, we need to make sure that our function has the appropriate form and cannot be evaluated immediately using the limit laws. We then need to find a function that is equal to h of x is equal to f of x divided by g of x for all x is not a or some interval containing a. If f of x and g of x are polynomials, you should factor each function and cancel out any common factor. If the numerator or denominator contains a difference involving a square root, we should try multiplying the numerator and denominator by conjugate of the expression involving the square root. If f of x over g of x is a complex fraction, we begin by simplifying it. Okay. Evaluating a limit by factoring and cancelling. Let me see if this works over here. Nope, it's not copied properly. What is this? Example 2.17. X square minus 3x limit square minus 3x this is as x approaches 3. To x square minus 5x minus 3. To x square minus 5x minus 5x minus 3 minus 3. So then if I plug in 3 over here, okay, and I will use my calculator for this. Three square minus 9 is 0. Okay. And then 2 times 3 square minus 5 times 3 is also 0. So it's 0 over 0. So can I factor it? Let me see. Do x square. Think can do this. No, minus maybe is this it? No, there's no square here. Or there is a square here and there's no square. There's no x here. No, that doesn't work. Two x squared. Maybe factoring doesn't work. Let me try another way. X square minus, it's minus 3x. Minus 5x minus 3. I don't know why this is not working. Um, then plus it with x. Oops, plus it with this. Think this is it. P, let me see. Wait, this was correct. All I had to do was take the x out. Okay, next one. What is this? By multiplying a conjugate. Root x plus 2 minus 1 multiplied with x plus 2 plus 1. And then the root goes away. Okay. Now what are they doing here? Yes, they're putting this all in one fraction, I guess. I think. So evaluate the limit from the negative side and from the positive side. Oh, since it does not exist on the negative side, then the limit from the negative side does not exist. Okay, this is new. I did not know that. Evaluating a two-sided limit using the limit clause. X is equal to 2 from the negative side. So 4 times 2 is 6. It would be 3. And then from the positive side would be 1. And then this wouldn't exist then. Oh, 5. Wait, hold on. Yeah, it would be 5. Okay, let's see what they did here. So this, the bottom would be 0. The limit has the form minus 1 over 0. As x approaches 2 from the left, the numerator approaches negative 1. We need to factor the denominator. Okay. Okay. Since x minus 2 is the only part of the denominator that is 0 when 2 is substituted, we then separate 1 over x minus 2 from the rest of the function. Limit of this is negative half and the limit of this is negative infinity. Therefore, the product has a limit of positive infinity. Okay. Squeeze theorem. Okay. Lim f of x is smaller than g of x, which is smaller than h of x. So g of x is like in the middle of these two. If you find the limit of f of x and g of x, and they're all going to L, then g of x and the limit of g of x would also be L. Apply the squeeze theorem to evaluate limit of x cos x. Okay, how would you do this? What are the two functions in this case? Okay, then, oh yeah, this goes to 0 and this goes to 0. Then x cos x will also go to 0. Okay. Evaluating an important trigonometric limit. In the first step, we multiply the conjugate so that we can use a trigonometric identity to convert the cosine in the numerator to a sine. Okay, and then we separate them, and then we get 0. exercises. In the following exercises, use the limit laws to evaluate each limit. Justify each step by indicating the appropriate limit laws. 83. Limit as x approaches 0. It would be 3, right? And then x approaches -2. 2 square be 4. 4 plus 3 is 7. And 6 times 2 is 12. So it's 7 plus 12, right? 83 and 85. The next one, 7. We'll just substitute it. Then for this, sine 0 is 0. So this is just 1. We're here. 2 minus 7 over 7. So it's minus 5 over 7. Yeah, 7 square 49. Then 89 would be 1 and then minus 5 over 7. What about the previous ones? 3 and then root 19. Okay, I think this one would be harder. So all of them would have the indeterminate form 0 over 0. We have to evaluate the limit. So for 93, question 93, x square minus 16 over x minus 4. X square minus 16 over, I think it's this, x minus 4. And then we do x minus 4, x plus 4, we get x square minus 16. So then this is equal to x. I think then the limit is 4 plus 4, 8. Question 93. Yeah. 95. 3x minus 18, 2x minus 12. Can take 3 out from here. So this is, okay, same thing over here. 2 over 3. 3 over 2, I mean. 97. T minus 9 root t minus 3. Uh, hmm. think I should multiply with this. And then I will get d root t. d root t three times 9. Shouldn't it be? I think it's easier if I do plus. So plus negative t and minus 9. Okay, that did not solve anything. Hmm. 97. Wait, how? How did you get this? t minus 9. Oh, I see. This is t minus 9, so this. And wait, I understand. So it's t minus 9 from here. Then divide this by t minus 9. That's how they got. Wait, next one. Sine theta tan sine pi tan pi. What is I keep forgetting. Tan pi is sine over cos, right? So then sine would be 1 over cos. And cos pi is 1, so the answer should be 1. Yeah, you told. Oh, it's a negative 1 actually. Yeah. So 1 over cos. It's just cos. Next. 2x squared plus 3x minus 2 and then 2x minus 1. Two x squared plus 3x minus 2. 2x minus 1. 2x minus 1. Right. Let me see if I can get something from here. Zero, and then 3x minus x is plus 2x minus 2. Okay. Ratio 8. No. This becomes 4. And then plus 2. Then this will be 4x 0. That means I think, nope. I made a mistake here. Wait. Hold on, something isn't right. Two x squared. This is 4. Yeah, but then that means this is equal to, we can cancel out 2x minus 1 and we are left with x plus 2. So half, 2 plus half is 2.5. Yeah. Use the method here. Okay, so initially it's undefined. Then I have to use those special methods. Do x squared plus 7x minus 4. x squared plus x minus 2. So it's supposed to be undefined, but I'm supposed to find it somehow. Direct substitution would be undefined. And I will have to define it from the negative side. Okay. Mm. Yeah, I don't know. Um, what if I take 2 out? No, that doesn't make sense. What if I factor both of them? There is a common factor. Hold on. X. This is wrong, but 2x squared. One of them is a minus. Is this 3? No, I think this is 2. This might be different. Yeah, I have no clue. Let's say the answer. 103. It just says negative infinity. Let's see how they did it here. Evaluating the limit of negative 2 from the negative side. Wait. Okay. I think I have to split the bottom, the denominator. To x. Yeah, this is correct. And after this is equal to x plus 2 to x square plus 7 x minus 4, then x minus 1. If I put negative 2 in there, if I put negative 2 here, I get this would be 1 over 0. So 2 times 2 is 4, 4 times 2 is 8. This is 18 over 3. This is a negative number. And this 1 over x plus 2. Wait. If I plug in 1 over should be positive infinity. This is evaluating to negative infinity. Because its graph is like this. It should be positive infinity, right? Or maybe not. This is wrong. This is negative 2, so minus. So 8 minus 18 should be 10. This is plus. This is negative infinity. Okay. Assume that okay, I don't want to do this. Let's just do this one. X approaches 6. So limit of these two separately. So 9 minus 4 would be 5. Root 5. 1, 1, 1. Yeah. Okay, I don't want to draw. Okay, next. Continuity. Continuity at a point. We see that the graph of f of x has a hole at a. Oops. F of a is undefined. At the very least, for f of x to be continuous at a, we need the following condition. F of a is defined. That's it. Oh, limit exists. Okay. A function f of x is continuous at a point a if and only if the following three conditions are satisfied. F of a is defined, the limit exists, and the limit is f of a. Otherwise, it is discontinuous. Okay. Determining continuity at a point. Condition 1. Determine whether this function is continuous at x equals to 2. it should be defined, right? Yeah, it's defined, limit exists. The limit is the value itself, so it can't be this. So this is false. So it's discontinuous at this point. And x equals 3. So 4 times 3 is 12 minus 8. It's 4, right? And then this is a minus 5, so it's not continuous. Yeah. Is this 1? Forgot what this was. Yeah. So it is continuous. Yeah. Okay. Types of discontinuities. A removable discontinuity. Discontinuity is a discontinuity for which there is a hole in the graph. A jump discontinuity is a non-infinite discontinuity for which there is a section of a function that do not meet up. So this would be a jump discontinuity. And an infinite discontinuity is a discontinuity located at a vertical asymptote. Okay. Continuous at an interval. Function is said to be continuous from the right if a at a, if a from the positive side, it's defined, and continuous from the left is from the negative side, it's defined. State the intervals over which this function is continuous. From negative infinity to minus 2, so defined at minus 2 and at 0, so there are gaps at minus 2 and 0. Okay. If f is continuous and limit of x approaches a of g of x is L, then you can put the limit inside. Intermediate value theorem. Let f be continuous over a closed bounded interval a and b. If c is any real number between f of a and f of b, then there is a number c in a and b satisfying f of c is equal to z. Okay, so the function is defined here. Then this is number c between them. Okay. Show that f of x is equal to x minus cos x has at least one 0. So between the interval 0 and pi over 2, it's below 0. So it's -1 and pi over 2. There must be c between these two that satisfies f of c is equal to 0 because the function is continuous. The exercises. The following exercises determine the points, if any, at which each function is discontinuous. Classify any discontinuity as jump, removal, infinite, or other. Okay, it's discontinuous at 0. It's an infinite discontinuity. This is also discontinuous at 0. Is there any other number? X over x squared minus x. It's also discontinuous at +1 and -1, I think. -1, 0 and +1. I think. Wait, are we allowed to look at the graph? I think it's. Let me see. It's all vertical. But I don't know if you're allowed to look at the graph. 5 e to the power x minus 2. So that would be like ln of e. ln of e times 2, I think. It would be discontinuous here. Yeah. So then would be 0 because 2 minus 2. I think it would be an infinite discontinuity, maybe 135. Tan 2x it's discontinuous at, wait, where is it discontinuous? Should be in radians at pi over 2, I think. Yeah, pi over 2, 3 pi over 2. Hold on. Pi over 2, 3 pi. No, it's not pi over 2. Wait. It's not this. Is it pi? It's pi over 4. Oh yeah, because it's multiplying by 2. and then 3, 5, 7. Okay. Decide if the function is continuous at a given point. Not continuous. It's probably a jump. No, probably a, what's it called? Removable discontinuity. 1, 3, 9. Yeah. Then for this, x at x is equal to 0, this would be -1. This would also be -1. I think it is continuous. Yes. Find the values of k. 3x plus 2, x is less than k. If I do k is equal to 1, it should be continuous, right? No. I need to find a value where these two are equal. So 3x plus 2, 2x minus 3. Something like this. X is -5. Is this correct? So 3 times -5 plus 2 is -13. And then same for the next. I think k is -13. Hopefully I'm correct. Yeah. So sorry, k is -5. Yeah, let's do this. I have to find the value of k. Okay. K is most probably 3. And that's just a guess. No, it's not 3. K, x plus 1. 3 plus 1, 4. And then it's probably this. Let's see. Yeah, 16/3. Okay, 161. This is continuous everywhere. No, not at t is equal to 0. This is false. It could be defined, but the limits are different. Okay. Oops. Don't know what's happening. And it's stuck. Okay, if it doesn't load, I might end the stream. It's lagging. Hold on. Oh, now it waits. Okay, let's do the last one. Prove the following functions are continuous everywhere. Hmm. How do I prove it? Like, I know what the sine theta graph looks like. But would that be enough? 173. Okay. For all values of a, f of a is defined and the limit exists, and the limit is the same as limit as theta approaches a is the same as f of a, whereas f of x continuous. Where is it continuous? Hmm. I think on all rational points, maybe. Nowhere. How so? Yeah, I think I need to think more about this. The precise definition of a limit. Let f of x be defined for all x is not equal to a or an open interval containing a. Let L be the real number, then this. If for every epsilon more than 0, then there exists a delta more than 0 such that if x minus a is between 0 and delta, then f of x minus L is less than epsilon. Hmm. Let me think more about this. Did I have a graph? Yeah. Definition of a limit is that as f of x approaches a is going to approach this number, then that means what? For every epsilon more than 0, okay, there exists delta more than 0. Ah, if the limit at f of a is L, then any difference between L and f of a will cause a difference between a and x. But why couldn't you do it the other way around? Why couldn't you do for every gap over here, there will be a gap here? Let me think about this. I don't know why it's stuck. Okay, proving that limit of f of x is equal to L for a specific function. Proof begin with the following statement: let epsilon be more than 0. Next, we need to obtain a value for delta. After we have obtained this value, we need to make the following statement, filling in the blank with our choice of delta. So choose delta, assume this. Next, based on this assumption, we need to show that f of x minus L is less than epsilon. Where f of x and L are our function. F of x and our limit L. So let epsilon be a positive number and then choose some random delta, let's say 0.5, x minus 1, so x plus 1. Thus, this 4x plus 1 minus 3 is for delta epsilon. So that means for every difference that exists over here, there will be a difference that exists here. For every epsilon, there is a delta. I don't know why this is not loading. Okay. Prove that limit x squared as x approaches 2 is 4. Let epsilon be more than 0. The first part of the definition begins for every epsilon more than 0. By stating epsilon more than 0, we signal our intent to do so. Assume epsilon is less than or equal to 4. Why do we want this? Why is it okay to make this assumption? In answer to the first question, later on in the process for solving delta, we will discover that delta involves the quantity 4 minus epsilon root. Forget this. Proving limit laws. Prove. Okay. Also, if you want to read any proof, I have them on a separate website I will show later. So let me go. This is my second website. Let it load. And you can basically, this website is dedicated for proofs. You can basically choose calculus. I don't know why. So everything is so slow. And basically this is for proofs. So if you want this, the sum law, you can click it and you will get the proof for it. And for this, I've written the proof for it. Okay, exercises. The following exercises write the appropriate epsilon delta definition for each of the given statement. Okay, I need this to load. Don't know why it's not doing. Okay. I don't know what was wrong with that tab. But first, I want to talk about the definition. Yeah. Why couldn't it be that when there's an epsilon, there's a delta? No, it is this case, but why couldn't it be when there's a delta, there's an epsilon? What I'm thinking is if you have a function like this, you have L A and over here negative A. Let's say delta implies epsilon, so some difference over here would imply some difference over here. But I think the problem with that is if we choose minus A, then there would be no difference over here, I think. So if we choose this, there is some difference over here. Over here we have a delta, and over here we have an epsilon. But if we choose exactly this, we would have a delta, but no epsilon. So I think that's why it's reversed. If there's an epsilon, there will always be a delta. Well, if I'm wrong, then someone can give a better explanation. Okay. Write the appropriate definition. 177. Limit g of t is equal to m. So let there be an epsilon such that minus m modulus is less than epsilon. That would mean there exists some delta such that the difference between t and b exists. 177. For every epsilon, there exists delta. Okay, so for every epsilon, there is a delta such that if there's a difference between T and B, which is less than delta, then there'll be a difference between GT and M, which is bit less than epsilon. Okay, f of x minus 2 is less than 1, then x minus 2 is less than delta. I would say like 1.8. What is it? 181. 0.25. Yeah, I mean like 2 minus 1.8. And but this one, f of x plus 1 is less than 2. Should it be minus 1? F of x, yeah, minus 1 is less than 2. So it's between plus 1 and negative 3. No, yeah, minus 1. So there is a difference of 2. So plus 1, between plus 1 and negative 3. So that means it should be between, so the x should be between should be 3 minus 1.5. Should be 1.5. 183. Why is it 0.39? Yeah, I have no clue. 3. Yeah, I don't know why it's 0.39. Or wait. No, it's 183. Yeah, it is 2. Looking at the wrong one. The following exercise uses the problem to prove the given one-sided limits. Okay. If epsilon exists, then delta exists such that now such that 5 is less than delta, then rho 5 minus x will be less than epsilon. Let's say 193. What is this? If um okay. I didn't understand this. Limit 5 minus x. I don't know how it got this. Let delta be epsilon cubed. Hold on. If for every epsilon there exists a delta. Okay, let there be a delta, which is let epsilon exist, and let there be a delta is equal to epsilon cubed. Then what? And epsilon is this. And if you square it, like this, you don't need modulus because it's going to be positive anyways. And then what? 5 minus x. Oh yeah, then this is delta, right? 5, which means as yeah, as x approaches y from the negative side, which means this basically. Okay, is there? What's next? Okay, I think that's the end of the chapter. I think I need to do more work on the precise definition of a limit. And I think I will end the stream here, maybe. Okay, I'll end the stream here. And next video we'll start learning derivatives. Hold on. Yeah. Next time I will start learning derivatives.